So today we'll be talking about a number of topics. Indeed, for the last few days, deep learning has been extensively covered. So what aspect I want to focus within deep learning is how to do it in a distributed manner, right? So how do we scale this up on multiple GPUs within the same machine as well as to multiple machines and keep a high efficiency? What are the programming frameworks that allow us to do this easily and at the same time have high efficiency? And then the other aspect I want to touch upon is how to exploit multiple dimensions that are present in data, right? So my research has focused on tensors, and those are extensions of matrices that we're all very familiar with. And I'll show how this framework can be brought into deep learning and holds promise for giving us gains in many different forms. So those would be some of the topics. But again, I encourage you to be interactive. I know this is early in the morning. I'm happy there is such a big audience. So since it's a long talk, I want you to not hold off questions till the end. So just raise your hand whenever you have a question or want to make a comment. Great. I mean, indeed, over the last few years, deep learning has touched upon almost every domain and improved performance. Right, so it started with image understanding when deep learning gave much better performance than other classical schemes in the ImageNet competition. And since then, we've seen it applied to so many areas. Speech recognition, natural language understanding, autonomous driving now, and increasingly more and more complex tasks. And of course, the canonical task which started it all was image classification and using a convolutional network. The idea is you have multiple layers of processing, and this helps out extract features in a more robust manner. The multiple layers help combine simple features into more complex ones and help us come up with an accurate way to do image classification. So as I said, the aspect that I want to focus on is efficiency and being able to deploy these large and complex networks easily and also in a large cloud infrastructure framework. So the example I've shown here on the top is the Inception V3 network. That's one of the state-of-the-art networks, right? So that's as you can see, without worrying about the details of what each block is doing, what you have is a very complex network, right? There are more than 100 layers, and there are complex interconnections between them. I mean, indeed, if I asked you to program this from scratch, that would be a non-starter, right? So having good primitives and a flexible framework for programming is quite crucial as these networks become very complex and has billions of parameters. Right? So indeed, even sending a single image through this network has billions of floating point operations. And that's why GPUs are the workhorses of deep learning, because they offer a lot more flops compared to the CPU. Right? So they're also perfect for parallel computation that these deep learning networks have. Right? So deep learning is nothing but a series of matrix operations with many nonlinear operations. And so how do we exploit the parallelism of GPUs to the maximum extent? And hence, through this, be also very fast in computation. That's one of the considerations. The other consideration is the memory, right? So especially as we deploy these networks on small devices, Like on Raspberry Pi, for instance, you do want more compact models. So how do you compress existing models as well as have frameworks that can trade off memory with computation in a seamless manner to give us the flexibility and portability across a range of platforms. So this is quite important as well. So we need frameworks that make it easy for us to do these trade-offs, right? So we want framework that is easy to program, right? That's the first part. Even complex networks, we should be able to quickly deploy. But at the same time, we retain the efficiency even as we scale up to hundreds of GPUs. And lastly, how do we enable good trade-offs in terms of memory consumption? So let's see how MXNet is a framework that scores high on all these aspects. So MXNet is an Apache open source framework, and we're actively developing on that at AWS. It started out as a university effort, but now is widely employed. In fact, there was a recent announcement last week of Apple Core ML being run on MXNet. So let me give you a brief idea of what MXNet is, but also compare it with other frameworks and look at the pros and cons. Right? So MXNet is like what we call the deep learning engine, right? So that's the one that powers these deep learning networks. And so some of the main features that are great about MXNet is the flexible programming paradigm. So I'm sure you've seen the imperative style of programming with the declarative style, right? So imperative is Python-like framework. So you just write your program line by line. It's sequentially executed, and so it's very easy to write that program, but it's bad for optimization, right? The declarative is the more involved style of programming because you declare variables, you do the compile process, so you get the computation graph, and based on that, you do optimizations. So these are the two frameworks, and what MXNet does is give you the ability to mix both of them. I mean, that's where the name comes from, right? So you mix both imperative and declarative style. And we'll see why this is an important feature. And we'll also see it has a lot of range of different language supports. So depending on your background, you don't need to stick to Python. You can use other frameworks such as R, Scala, MATLAB, JavaScript, right? So a range of different languages. And the most important part is the backend. So it's highly efficient and is able to auto-parallelize and get good efficiency on hundreds of GPUs. Right, so let's start with some of the frameworks and compare them. Right, so what I've shown here is an example cafe program. And so if you're trying to deploy a ResNet here, you describe what a layer is, right? So you use the protobuf format. And this is just like kind of part of the code, of course. There are about 4,000 lines of code here. And so, this uses protobuf as an interface. And the nice thing about that is it makes it portable. Yeah?
You mentioned the protobuf formats, and I think many people won't know what the protobuf format is.
Yes.
Can you explain just a little bit about writing protobufs? And, yeah.
OK. So, I mean, protobuf, to give a brief idea, right? So it's a standard format. So what you do is you can, have number of types, like what each type is, and then specify that as you go about. Yeah. So just very brief, but I can get into because I mean this is really not the main focus. So. I encourage you to look further if you're interested. I mean, the only point I want to make is that makes it portable, but at the same time, it is kind of not very clean to write that. It's messier and it requires expertise. Like you need to know what protobuf is. So that's one of the points. Like if you don't know protobuf, it's not easy to write. So, on the other hand, there's TensorFlow, right? So TensorFlow is very popular. It has a very rich set of operators, so you can get easily started and start writing programs without, having to code that up yourself. One of the downsides is if you're not an expert programmer, this can be tough. For instance, what I've shown here is the beginning of the implementation of Atom, right? So Atom is the optimization that's adaptive, and you can see that you have to declare variables. You have to like simple kind of update operations get quite messy to write. That's because it's not Python-like. It's a declarative style of programming, which is great for efficiency, but harder to write this. And so that's why most beginner programmers would be going for Keras, because now this is a higher level API, and you can use different backends. So it started out with the TensorFlow backend, but now we also have MXNet backend for Keras, right? So the great thing about Keras is now you can see it's very easy to define a network, right? So you're saying, let's add a dense layer here, and let's do dropout, and let's add one more dense layer, and so on. So, yeah.
How, in TensorFlow, how do you take advantage of parallelism once you say use?
Yeah, so in all the frameworks, we'll see it's the compute graph. So once you can get the computation graph, you can go ahead and do a number of optimizations. So I'll come to that. That'll be the detail of the talk. I'll show how it's done in MXNet, but a lot of these features are kind of quite common for a compiler, right, to do. But now how do we do it at scale is the challenge. So I'll come to that. That'll be the main kind of part of the talk. But good point. So there is this Keras, right? So Keras makes it easy, but it only separates a small number of operations compared to everything that's out there. Meaning, especially if you're coming up with new architectures or new frameworks, it's quite difficult to, you have to write that into Keras, right? And that's complicated. So Keras is great if you want to use the existing frameworks, but if you're a researcher or if you're a developer coming up with something new, this is hard. Right? So again, PyTorch is another popular framework. So you can code in Python, which is great. It's flexible. But again, when it comes to performance, for more complicated programs, it tends to be slow. Right? So again, all these frameworks are in the development process, so much is also getting to be better as we go about with this. But as you can see, the PyTorch has a much simpler way to write programs. So you're a Python programmer, you can immediately get started. Right? So how does MXNet compare to all this? So what MXNet gives you is this combination, right? So it gives you both the imperative as well as the declarative style. In the earlier frameworks, you had to choose one or the other. So for instance, if it was PyTorch, it was only Python-like, right? So meaning it was only imperative. If it was TensorFlow, it was completely declarative, right? So you couldn't choose one or the other. So what MXNet does is it combines both of them. So in this example here, the Atom algorithm, right, is written in imperative style. So you can see what you're doing here is setting what the learning rate should be, right? And this is the update equation. So you're updating the weight using this learning rate framework. As you can see, it's literally just 2 or 3 lines of code, right? So this is how you would just think of what this update is and write that. So this is the imperative style. But if you want to define the network, you can do it in declarative style. So declarative style means you're declaring symbols here. So that's why you're saying, like, no, I want the batch norm, so I'm declaring the batch norm symbol here, right? So I'm doing batch norm on the data, right? So that's the first part. Then I have the activation, I'm declaring the symbol for activations, and so on. And so as you can see, like, what is the benefit of doing this, right? So the benefit is you want to be able to write in imperative style for a lot of these update equations, which do not actually require a lot of optimization. So most of the optimization in terms of memory and parallelism should be done on the network architecture, right? So that you can write it in declarative style. And these update equations, you can write it in imperative style. And so by being able to mix the both, you have the maximum flexibility, right? So with this, it leads to much shorter programs, much easily readable programs, right? So you only declare symbols when you need this optimization. Yeah.
Just a question. So in MXNet, for instance, in TensorFlow, if you want to implement, let's say, second-order algorithms, you have to sort of circumvent only having one. So when you call a run call, that's once and then everything's cleared off.
Yeah.
Is this different? And it allows you to store up sort of more variables and update variables quicker.
Right, so that's a good point. So you can, right, so there is a way to also store variables or do further manipulations if that's what you're asking. Yes, that's possible. Yeah. By the way, I can't see very well with these bright lights, so speak up. Otherwise, I won't know that there is a question. So that's what MXNet gives you, this flexibility, and that's great, right? Because you get now both efficiency as well as the flexibility of programming. But we were not content just with that, right? So that's why I'm saying this is still kind of hard for some of the beginner programmers to do. So what we went about asking is, can we make it even easier to do this? Because we are right now saying, write in symbolic style or declarative style if you need good performance. But is there a way to automate this process? Meaning, you write only in imperative style and you can generate symbolic graphs as you kind of call a function. And that's what this new framework called Gluon is on top of MXNet. I mean, the idea is we want to combine the best features from all the existing frameworks, right? So to give the maximum flexibility as well as performance. So let's see what the Gluon framework is, right? So this is an example of Gluon. As you can see, it has a Keras-like feel, right? So it's very simple to start defining the network and writing what the network should be, right? So here you're saying add a dense layer, add these multiple dense layers, and there is a loss that you define, and you can, with AutoGrad, do the backward pass, and you kind of define what the batch size is and do training on that. So you write it completely in imperative style, but there is this function called net.hybridize. So this hybridization converts the imperative to symbolic execution. So the idea is now that you have the symbolic graph, this becomes portable. You can go from one programming framework to another. You can go to different architectures. And so that's the the best of all the worlds, because you have the ease of programming. You can write very simple programs, and at the same time, be able to get very good efficiency. So let's see some details about how the backend works, right? So far what I've shown you is you can quickly write programs and still be able to get high efficiency. But what are some of the principles behind this? So as I said, so what you're writing in the front end looks like this, right? So this is the ND array. So ND stands for ND array. It's a multi-dimensional array. So you're declaring, say, two arrays here, multiplying, doing some addition, right? So some very simple operations. And you can represent it as this symbolic computation graph, right? So this is so if you just wrote it in Python, right, you would get no graph. But what the Gluon framework does is, you can generate the symbolic graph. So it converts it into symbolic operation. So what you see on the right is not what you are writing, but this is what MXNet does in the backend with Gluon. So, as you can see, writing it in the declarative style is much more involved. It's kind of harder to read. But this is what Gluon automatically does that for you. It can generate the symbolic graph even as you write it in imperative style. And once you have the symbolic graph, you can do a number of optimizations, right? So we'll see how we can do memory optimization. We'll do operator fusion for increasing the parallelism. And we'll also see how we can do auto-parallelism with the computation graph. The core is really this computation graph, right? So if you don't have this, you are really in the dark. You don't know how to optimize this deep learning framework or this program. So, but the key is, in order to write for this computation graph, you need this symbolic style of programming that's just messier to write. You have to kind of be careful. You have to declare all the variables, right? It makes for longer programs. So the Gluon framework automatically does that for you.
Are there then a set of constraints on the style of imperative code that you can write in order for it to be translated into?
So right now it's Python.
Okay, anything in Python?
Yeah. So again, those operators need to be there in the backend, right? So otherwise you have to go and define the operator. That's true in any of the frameworks. Yeah. Yeah. What? Would you speak up, please? Right, so you want to write very simple programs, so the programmer should be able to write it in simple imperative style. At the same time, the backend gives you high efficiency. So how do you enable that? That's the goal. So anybody who's writing deep learning programs. Sorry, I didn't hear Scala. I'm not sure I understand. So you're saying give all the support to the language? By the way, even Scala is supported in MXNet, right? Not with Gluon, but you can still use that. The idea is to be portable. Like once you have the symbolic graph, you can also go ahead and execute it in Scala. Okay. So anybody writing in Python, right? So. Sorry, energy too. Could somebody repeat? I'm not able to hear.
What I'm trying to say is why spend all the energy trying to converge different languages? Why don't we just, for example, optimize scalar so that when we want to do deep learning, we know we're using scalar?
So I'm saying MXNet supports all those front end anyway. So it's the back end you want to optimize. Right. So what's the alternative? I'm not sure I understand.
Is it possible maybe to take it offline? Like maybe one-on-one?
Yeah, sorry, I'm not sure. So, I mean, the idea is really, I think, is it clear for, okay, good. So let's now see what the backend actually is doing, right? So how do we, once we have the computation graph, how can we further utilize it for doing these optimizations? So for memory optimization, the idea is by traversing the computation graph, you can do better memory allocation, right? So in this simple example here, for instance, the aliveness. I mean, does this variable still, is it really there in the scope anymore, right? So the idea is now once A gets processed into B and C, right, it's no longer needed, so you can delete A, right? So all these are very simple and kind of quite classical, things that you do during compilation, right? So also, like asking which variables can share the same space, right? So because A gets overwritten with B and B gets overwritten with C. So you don't need a separate piece of memory for this. So these simple memory optimizations you can do once you have the computation graph. And so some numbers on how even these kind of simple frameworks can help get much better memory requirement for many of the deep nets, right? There's the AlexNet, the Inception, the VGGs, and you can see that now with memory optimization, you do get several X improvement in memory, yeah.
Sorry, the baseline, was that based on CAFI or?
So the baseline was just without the memory optimization, right? So you don't use the computation graph and don't do any memory optimization. All right, so any framework that does not have access to the symbolic graph would not be doing this. And so you can see that you can get memory improvements doing this. You can actually even do much more than that. Once you have access to the computation graph, you can trade off memory for computation, right? So as we said before, like based on the computation graph, you can decide what to store, right? So in this example, what we are showing is how you can just recompute some of the quantities and thus reduce the memory requirement. So the example here is, there's a forward pass and a backward pass, right? So this is the standard, like a deep network. So during training, you do both the forward and the backward. And so, baseline, like you would store all these activations, right? So every activation that you compute in the layer as you go through the forward pass, you would be storing all of it. But now with this trade-off, what you do is you don't store everything. You divide into segments and only store the head of the segment in memory. And so now for the backward pass, for the ones that you are not stored, you just recompute this, meaning you start from the head, you go through part of the forward pass again and just recompute this, right? So the idea is, in many cases, if the memory is the bottleneck and computation is not, you can afford to recompute, but at the same time, you can get away with much smaller memory requirements. In fact, the memory requirement can reduce to as little as square root of the number of layers, right? So especially if you think about these very deep networks like ResNet or Inception v3 with hundreds of layers, there is a big reduction in memory by doing this process. And so you can, easily do all these trade-offs once you have the computation graph. And just some numbers on how you can get now reduced memory requirements. So you can, try different number of layers and see what the memory is like with no optimization versus with this optimization where you're doing the trade-off between memory and computation. And for instance, in this example, the computation cost increased by 30%. But if this is something that you can live with, but you have much more constraints on memory, you can go ahead with this. Right, so the idea is once with the computation graph, now you can think of all these very interesting trade-offs and optimizations to do. Yeah, Shakir.
Can you say a little bit about RNN models instead of feed-forward confidence, and when the graph is doing the optimization, is it doing it automatically because you need to decide where in the graph it's going to cut and how to do the backward when you redo the computation?
Yes, no, that's a very good point. It's not automated because we want to give the flexibility, right? So we want to say like how many segments do you want and what should be the trade-off. So again, if it was a specific maybe architecture with memory constraints, we could automate it. But we haven't because there should be flexibility for the programmer. So I think in a different slide, I also had the numbers for RNN. So there are experiments run even there, and you can have a big reduction in memory. I mean, especially since there, right, the memory can be quite big too. Yeah, good point. Any other? Yeah.
Are you considering any overhead of this optimization?
So as I said here, there is the computation overhead, right? So you do increase the computation cost by 30% in this. No, the graph is anyway being generated, right? So the idea is without generating the graph, you cannot do any of the optimizations. You can't, even do the simple memory optimizations. We'll see you can't do auto-parallelism. So you need the graph. And I'll show some example notebooks where without the hybridization, meaning without generating the graph, the performance is much worse. So you get the boost in performance by generating the graph. So mostly, like, even though there is some tiny overhead in generating the graph, it is much better to generate the graph. Because without the graph, you really, don't have the ability to do any of the optimizations. Yeah.
Since you're doing these optimizations by hand, they're not automated, does the framework provide tools to ensure that you're not doing something that causes your algorithm to be superlinear or for you to lose information accidentally?
Right, so I want to clarify, only this scheme is right now not automated, right? So if it's like all these like base cases, this is automated. So this, you don't have to do it by hand. And this really depends on the framework, right? How much extra computation you want to tolerate and what's the limit on your memory. And that's why it's more of like something that you want to tune for. But yes, I think in future we want to make the tools be easier to do it, but at the moment it's something, I think it requires some expertise to go and check out these different points in the trade-off and see where you get the best, for your setting, where the best point is. Yeah.
Do there exist profiling tools which we can just run and see what part of the graph or what part of the program is like?
Right. So there is an MXNet profiler, and I think so they're defined in the notebook. So I'll show you some of the notebooks. So you can profile, you can checkpoint, you can get these various numbers. Yeah. Yeah.
Can you get feedback after the optimization on how to improve your code? If you write code in a certain way, you make it persistent.
Right.
Mistakes, and after the optimization, you can also give feedback on how to get better.
Yeah, I think that's an area of research, right? So we're all trying to essentially get the deep learning to do our programming ultimately. So that would be the holy grail, and there is indeed research, getting towards the direction. But at the moment, not in this context, right? So it can be quite complex, like especially if we go to the level of kernels and see why there is no improvement or why there is for specific operations. So it's still an involved process. But the good news is most of it is done for you, and you can now go ahead and use the framework. Right, so the other aspect is to also enable operator fusion. So if you have the computation graph, you can get an idea of how to, there are lots of operations that happen, right, one after the other in the sequence. So you can come up with ways to fuse the operator. So basically the idea of fusion is, again, like you kind of have this kernel that can better parallelize these operations once it's fused. And so that's, so for instance, the atom, if you make it as a fused operator, you get like about 20% improvement in performance. So again, this is something that Gluon does this automatically for you, and you don't have to worry. Right, so otherwise, this is a hard one. I think there was a paper on dynamic batching on recurrent nets with operator fusion. So if you're trying to do it manually, it can be quite involved. But since this is automated, you get the performance boost without having to work for it. So I think that's great. Right, so the next part is auto-parallelism. Like, how do we make sure these parallel programs have high efficiency? Right, so you can keep increasing the number of GPUs. Like, especially if you're in a company, you can kind of get more and more, right? But even otherwise, the question is, I'm so sorry. I should not be waving too much. Let me see. Can you hear me? Yeah. Great. So, writing parallel programs has traditionally been very painful, right? You had to be an expert in MPI. You had to know like every operation, how to go about and ask how to distribute it to different processors, right? So I've shown a very simple example here. There are 2 GPUs and a CPU, right? And what you're doing is you're doing local computation, so you're doing the forward and backward pass, and then you're sending the gradients back to the CPU, so the CPU is aggregating the gradients together, right? So you can see it's already quite complex, right? So it's all, with just these few layers, you have to send like gradients from every layer, you have to do the forward and backward. So of course, you don't want to write this in MPI, right? I think no one wants to do that. But on the other hand, the benefit that MPI offers is like flexibility. So if you're an expert, you can get very high efficiency because you can specify, how the communication should occur between these different processors, right? How to, get high efficiency. So the question is, can we get this for free? Like, can we have a backend that automatically gives you high efficiency even as you scale up to possibly hundreds of GPUs, right? That's what we'd like to explore. So what MXNet does is auto-parallelism. So again, this is a simple concept. So you have a computation graph. When there is branching, you know that the 2 parts can be done in parallel, right? So just from like traversing and analyzing the graph, you can immediately decide what to auto-parallelize, So this is one of the first things you do once you have the computation graph. Right? So in this example, these two branches can be done in parallel. So you execute it in parallel, and then, of course, when there is merging, you need to communicate together, either between cores, between processors, right? So parallelism can occur at different levels. Right, so the popular form of parallelism is the data parallelism. Right, so this is quite a natural setting where you have lots of data, but you have a model that fits in each processor. So typically, a processor for us would be one GPU, right? So we want to scale up across multiple GPUs. So what we do is we'll distribute the data into different GPUs, right? So each GPU will have its own batch of data. So it will do a forward and backward pass and compute the gradients locally, and then it will aggregate that together. So through a key value store, you can now pull all these gradients together, aggregate, and push it back to each of the local processors. Right, so it's, yeah.
Is the complete training done in each one of those? Or do you go up and you aggregate and then have to?
Yeah, so it's at the end of each batch. You have to do aggregation, you come back. Right, so this is the data parallelism, and this is the most popular form because you could have these. And the other form is the model parallelism. That's more involved if you have to split the model across different processors. So let's first see this data parallelism in more detail. Right, so this is again data parallelism, but taken to multiple machines. Right, so earlier we thought about multiple GPUs in the same machine. If it's now multiple machines, you also do the same with network. Right, so there's a network, there's a key value store that's distributed across the network. So that's over multiple machines, but it's still the same principle. Right, so nothing changes in terms of the principle, but what changes is where you keep the key value store. So now it's distributed across machines. Yeah.
Question. I want to ask, as it stands, how rich is the set of operations which are available in MXNet or Gluon? And would someone who is looking at doing parallel computing in general, rather than specifically in the machine learning context, would this framework be interesting to them as an easy way to write imperative code, which then is translated into parallel code?
That's a great point. I mean, we're continuously adding more and more operators, right? But at the same time, if you're looking for something outside the realm of popular deep learning, it may not be present. But there's one more new framework called TVM. So I didn't put it in the slides here. So TVM lets you define operators very easily across different frameworks. I mean, you can also bring that into PyTorch. You can bring it to other frameworks. But the great thing is, you can write now operators for your GPU without being a CUDA programmer. So it gives you a Python-like interface. It gives you the ability to define memory layouts, data reuse, and so you can go ahead and do further optimizations in each platform. But this is portable across platforms.
Because I think that in some respect that talks to the question earlier about why not focus on optimizing Scala or whatever. I think part of the thing is that it's difficult to write code, which is, to conceive of a particular set of operations on data in Scala, you've got to really think about it carefully and think about how to think functionally.
Right.
And so you're getting all that for free potentially, and as this library of functions grows,
exactly.
You can do more stuff potentially add your own language.
Yeah, no, exactly. And in the second part of the talk, I'll talk about tensors and how we're adding those functionalities, right? So that gives you some idea of adding new ones, not just using the existing ones. But for really low-level optimizations, if you want this to run very efficiently on, say, GPU or ARM architectures, TVM is the framework that makes it possible. Yeah. So Spark is, again, not, I mean, in principle, it's, again, like you can do key value store and this kind of distributed computing, right? But where this course is getting very high efficiency on multiple machines for the framework of deep learning. So I'll show you some numbers. Yeah, so I mean, first of all, Spark does not run on GPUs, right? So that's already a very big benefit. And also the overhead in Spark is really high. I mean, people have shown, like, I mean, the data structures are quite bulky. Like, even doing some simple things gives you several X improvements. So there is I mean, it's great to get you started, but it's really not good for efficiency. Okay, great, yeah.
So, also, this is great, but the thing I keep on seeing, that it's great for tuners. People are going to go in and tune all these different kind of things that you get now.
I mean, you don't need to tune, right? It's already done for you.
Like, because you also have options that, like, you're going to have to choose whatever amount of GPUs, you're going to have to trade off with this, like, your computation versus your memory.
I mean, that's one example, but if you don't want to do it, you don't need to do that.
That is the point of saying, like, what have we learned, especially kind of when, like in Hadoop, it ended up being that everybody's just going to have this default, right, that comes with the thing, and then everybody just uses that, and it's so hard to know what the kind of witchcraft that, so that's what I'm seeing again. So what did we learn from Hadoop as we're doing this?
I mean, so you can use profilers and try to take into each of the consumption and look at that, right? But indeed, like once you go lower level, it gets very complex, right? So there is like kind of, it sometimes is even counterintuitive how things change. So, I mean, that's still a hard process, right? So the key is like for a big range of operations for deep learning, this is now done for you. This is, you have an efficient framework.
Which is better, MPI or
I mean, so MPI is just not feasible, right? So even the most expert of an MPI programmer cannot scale it up to hundreds of GPUs on these networks that require billions of operations. Right, so this is just not feasible. I mean, if you had a magic programmer who could write every single optimized code on how these communications should occur, that would be ideal, but you know, we can't do it. It's both, right? So you want to make the front end as easy as possible at the same time, get high efficiency on the back end. So it should be both. So both. You need both, right? So otherwise you cannot, if the front end is too hard to work with, people won't use it. On the other hand, if the back end does not give you efficiency, the whole point is lost. You need both.
Does this framework support a mixture of different devices? So if you had different NVIDIA graphics cards or API?
Absolutely, yeah. So you can do that. I'll show you like in the notebook. So it's very simple. You define different contexts and you say like, you know, which part of the data goes where, and that's it. Okay, so what are some optimizations we do with this distributed parameter server, right, or this key value store? So the main one is having this hierarchy. So at the lowest level, we have the GPUs, right? So communication between the GPUs is quite fast. So you have this high-speed PCIe bus. But going back to the CPU is slower, and of course going through the network will be even slower. And so the idea is to do all the aggregation locally within the GPUs and only then communicate to CPU and beyond. Right? So inter-GPU communication is getting faster and faster with each generation of GPUs. So in the latest Volta, it'll be even faster. And so we have the framework that exploits it because you designate one of the GPUs as your local server, you do all the aggregation within GPUs, and you only communicate the aggregated data or the aggregated gradients to your CPU and beyond. And so that's actually one of the big reasons for the savings we obtain. Yeah, so now we show some experimental results. So we'll see, we'll vary the number of GPUs. We'll also vary the batch size, right? So how much data do we put in a batch for each GPU? And see the scaling behavior. So this is with the ResNet model. This is on the P216X large means you get an instance with 16 GPUs in it. They're the K40s. And this is just the mini batch SGD and synchronized operating. So there's also asynchronous option if you want in MXNet, but this one is synchronous. And so here are some numbers. So this is the time taken to process one batch. Sorry, that's a typo. So, yeah, apologize for that. So, the idea is, there are several curves, so let me break this down for you. Let's first focus on the different batch sizes, right? So, as you see here, the batch size is increasing, right? So you're going from 2 to 4 to 8 to 16. So indeed, the time taken to process a batch should be doubling because you have more data per batch. So it's not surprising that this is kind of increasing as you go up here. So what's more interesting is how within the same batch size, as you increase more number of GPUs, what happens to the time. Right? So this is batch size per GPU. So as you add more GPUs, you would be increasing the total batch of data, right? Because you're now getting a fresh GPU and adding more data to that. And so you expect this line to be as flat as possible, right? So because the idea is the time taken to process a batch should ideally be the same no matter how many new GPUs you keep adding, right? So that would be 100% efficiency because you have no overhead at all in this ideal scenario. You keep adding new GPUs, right? The time per batch is the same, but of course you're increasing the total batch in your iteration as you add more GPUs. And you can see that for large batch sizes here, so batch size of 16 per GPU, it's more flat, right? So there's only like kind of the increase by like 115x as you go from 1 GPU to 128 GPUs in this example here. But with lower batch sizes, the curve is more nonlinear. So the idea is when you have a small batch size, right, there is more overhead. And that's intuitive, right, because you're spending more time on communication. So you're communicating these small batches of data, there will be more overhead. And so for efficiency, you want to keep the batch size as large as possible, right? So, but what is what's preventing us from doing that? So right now, it's harder to train with larger batches, right? So this is, I think, something that people have done research in a number of papers. It's also harder to generalize with larger batches. So if we come up with better training mechanisms, then we can exploit the efficiency to the fullest. I think in the examples, like I think 16 was something that we could go to. But it's really now not the hardware that's preventing us, but it's our training algorithms that prevent us from utilizing the best possible efficiency of these systems. And but that's something interesting as an open research problem. Right? I mean, indeed, you observe that if you look at the convergence plot for different batch sizes. So this is the, I think this is the total batch size. So, and you can see that as you go to this larger batch size, you pretty much, you have to increase the learning rate, and you kind of do this like decrease at certain epochs, right? So this is kind of standard, like you have these fixed schedules of how the learning rate should decrease. So you do this strategy, you can get to a good validation accuracy, but you do see like it's less stable as the batch size increases. So this is still a delicate matter to be able to train with larger batch sizes. But I think any research in this direction will vastly improve our ability to train models faster on a larger number of GPUs. Right? So, and MXNet is a framework that now allows you to do this with high efficiency. And so the goal is, now, indeed, as we can harness the power of more GPUs, we can drastically bring down the time that it takes to train. Right? So if you used only 8 GPUs, you would need about a week to train on ImageNet. And now with 160 GPUs, it's half a day. And we'll have to really test where the limit is, right? So as I said, the limitation to go even further, I mean, you can get 1,000 GPUs on AWS, but the challenge is how do we train on these larger batch sizes? So if we can resolve this, we would, who knows, maybe one day we'll be able to train ImageNet in a minute. So that's the goal. Any questions here? So let me show you some Jupyter notebooks that covers many of these concepts. So I will not, go into details, but I just want to kind of show you the website and what's available there. So Zachary Lipton in our group, he's been the primary contributor for this, but it's really a community effort. There's been a lot of contribution from others as well, but he's managing the overall course here. So this is very accessible. It does not assume any background in deep learning. Yeah?
Just a question. As a researcher in non-convex optimization, what do you think are the most promising big batch methods going forward to increase the training time or decrease the training time?
Right, hopefully decrease. But I think the question about how you can get good regularizations, right? I mean, whether we can understand the implicit regularization of SGD and now make that better even as we have these larger batch sizes. That's one important point. But also the other is, do we have better hyperparameter optimizations that allows us to come up with good learning rate schedules? That's another one, yeah.
So do you not see any sort of progress in second-order methods?
So second-order methods, that's something that I've studied, and there's a lot of very nice theory there. The hardest thing has been to make it scalable. So now there is some movement in the inexact Hessian methods. So I do find that promising, but none of them have been, really extended to a large-scale framework, and I think there is still a big challenge there. Yeah. I mean, so Moore's law is, of course, helping us, right? So it's increasing our computation capability. So that's why, we can now build bigger networks and have more processing power. So, it does help us. So I'm not sure if you had anything else specific in mind. Sorry? Yeah, so I mean, as we can, get access to better GPUs, right, that will only, help us do this faster, more efficiently. So yeah, so that's, yeah.
The website address?
So yeah, so this is gluon.mxnet.com. Yeah, I guess you can't see, it's tiny font at the top there. So, or you Google deep learning straight dope, it may show up. So that's what Zach likes to call it. So it's very accessible. So there's like from first principles you get introduced, to like you can do linear regression from scratch. You can do all these basic networks. But you can also, there are many advanced topics as well. So there is, I'll show you some of these multiple GPUs, how we can do, and the hybridization process in Gluon. And we're adding some of the advanced applications as well, like trial STMs, object detection, GANs. So this is a growing set of tutorials. And the good thing is, because they are Jupyter notebooks, you can just run them, right? So you can make some small changes. You have your own data set. So I did this locally now because I wasn't sure of the network. But if you're interested in running them, write to me. We can provide AWS credits. And also, if you have some project ideas, we can help you with that. So here, I want to show this notebook that is talking about hybridizing, right? So what I mentioned in the slides was, like, you want to write in the imperative style, and it automatically generates the symbolic program or the computation graph for you, right? So that's what the hybridization process does. And in Gluon, it's very simple. You define this as a hybrid sequential block, right? So when you're writing the network, so in the examples I showed, it's the same way, right? So there's no difference. The only thing is you declare it as a hybrid sequential block. Otherwise, you define your program as you did before. There is no change at all. And so now when you call the hybridization process, what it does is it converts it into a symbolic program. And here the example times you can see after hybridization, you do get a boost in performance. So you should always hybridize, and if you care about efficiency. So that's what this simple test is doing. And you can check now for your symbolic program, right? Because now you can, if you declare your data as a symbol, so what you're having input to your program is symbolic, and you obtained after hybridization the network that's also symbolic. You can output this as a JSON file, right? So JSON, you can kind of look at the symbolic specification of your network. So you can see here, that this is the dense layer. So this is like what type it is, right? The shape, everything is automatically inferred. So you don't have to do this. It's done for you, right? So, 0 here means like it's not specified yet because it depends on the size of the input, right? So there is, so you can do this now. So all this is now you can automatically generate, right? Of course, if you thought about writing this, this would be too involved. But like the simple imperative program you wrote, you can obtain this symbolic graph, right? So once you have this symbolic graph, you can port it to any of the other languages. Could be C++, R, Scala, right? So you can run it on other programs. Yeah, so you can save the model and the parameters. And yeah, so this is kind of going into more details, like you can do the same with hybrid block. And depending on if you fed the NT array, that would be the imperative style. But if you fed it a symbolic input, that means it's a placeholder for symbolic execution, and it will generate the symbolic graph. So it's really as simple as that, right? Like you define your imperative program, and say hybridize, like declare it as a hybridization block, and you can obtain the symbolic graph and a better performance. Any questions here? Yeah.
Is there any way we can visualize the graph after we've produced the graph? Is there any way we can
Yes, yes. So there is the, with the MXNet profiler you can do, yeah. I mean, in this example I didn't show, but yeah.
And after visualizing, if you're not satisfied with something, can you like directly modify it on the graph?
Yeah, so you can go back and, yeah, you can directly modify that graph, yeah. Yeah, that's the benefit you get with this. If you are kind of, an expert and want to do further optimizations, you can go ahead and do it on the graph. Yeah. Any other questions? Great, so that was with respect to hybridization. So let's now see how to train on multiple GPUs with Gluon. Right, so this is again a very standard convolutional network. It's very easy to define that, right? So you have the convolutional layer, max pooling layer, another convolutional layer, and so on. In the end, you flatten, you do the dense network, or the fully connected layer. So there is the loss function, and now when you want to train on multiple devices, so this is as simple as this, right? So this is the only new thing. You define what your GPUs are. So in this example, there are 2 GPUs. So this is 0 and 1, right? And you initialize the 2 GPUs, and you say what the input data is. In this example, it's mnist, right? And there is the split and load command, so it automatically does the splitting for you. So that's pretty much it, because everything else is what you would do with a single GPU, the other parts. So the details here, you can see the plots, but this is really about what you would do even with a single GPU, right? So none of that changes. So going from like a single GPU to multiple GPU is literally a line of code, right? So you define what your context is, and this context could also have been CPU, right? So you could have also done some computations on the CPU, so you just provide that as an additional context. So you provide this context, you say split data, everything else is taken care. Any questions here?
Yeah. With regards to adding GPUs, how does the law of diminishing returns affect things? So if you had an infinite number of GPUs, would you start to notice that you would need to increase the number of GPUs to get the same kinds of...
Yeah, so the bottleneck is also communication, right? So ideally, if you had all this infinite number of GPUs on the same board with high bandwidth, right, then there would be less of an effect of communication bottleneck. But like right now, we only have 16 GPUs in a board, and you have these interconnects. And those interconnects are also getting better, but there is still, that's the bottleneck, right? So the communication starts getting worse as you increase the number of GPUs.
I mean, on that previous set of graphs that you had 20 times as many GPUs and 18.8 times speed up, right?
Yeah.
Where is that?
Overhead, yeah. Yeah, no, exactly. There will be some overhead. The question is how can we reduce it, and large batches also help you overcome them. Is there a question there? Okay, no. Great, so this was with multiple GPUs. Now if you want to do multiple machines, there is just a little bit more. So the idea now is you have to kind of define this key value store and specify the push and pull across multiple machines, right? So it's a bit more involved compared to a single machine. So as we showed before, the idea is there are now this hierarchy of multiple GPUs within the same machine, but now through the network, we connect to multiple machines. And so the KV is the key value store. So you create your key value store. So in this example, first we do just the local, just to kind of show you the intuition. And you say, like, what is the shape, like what are the dimensions of this, right? And what you should initialize there. And So again, as before, you define the contexts, and you pull the existing key value store. So meaning from the key value store, you pull it to individual GPUs, so you see what the current value of the weight is. And you can make some changes locally, and then you push, right? So it's store.push pushes it back to the key value store. And so you can do this push and pull commands, and that's pretty much it. And so with the distributed one, so that was with the single machine. So even with the single machine, I mean, in the earlier code, you didn't have to do this because this was done in the backend, right? So you didn't have to explicitly say, do the push and pull, because Gluon already wraps that around you. But with multiple machines, you have to kind of specify this. The only thing is you create a distributed key value store. And then you can do the push and pull commands across this. So what you do is you distribute the data and you do that. So as you can see, multi-machine is a bit more manual, but not much more complicated than before. Any questions here? There? Yeah.
And like the architecture you give it, like the way you are proceeding, where you have several machines. If you are in the context like the Hadoop context, where you have like the name node, which is the name node, and have the worker node, can you apply this? Can you use this method from this one?
So I mean, it's the same principle, right? So as I said, the key value store, the push and pull, it's just a very simple operation. But what's important is not to introduce a lot of overhead and do this in a lightweight manner. But it's the same principle.
Just thinking that you have any kind of fault tolerance kind of like one of the GPUs or one of the...
So in one of the earlier versions of key value store, all this is available, right? So you can get the full version. But for deep learning, honestly, they just kill performance and it's not needed, right? So there is, I mean, even say a machine fails, it's not the end of the world for deep learning, right? So you can go ahead and, use the gradients from the others and keep training further. So for most of these, many of the classical systems frameworks, right? That's why are not very suited for deep learning, because just the paradigm is different. We don't worry if we lose some gradients. Even if we lose some precision, it's okay, right? So that's why it's many of the systems principles, we should kind of, by leaving them behind, we can do a much better trade-off between performance and the resulting accuracy of deep learning. It's a different game here. But yeah, the full version is available. If you are interested in a key value store with all those bells and whistles, that's available. But that's not what's used in this framework. Okay, so shall we proceed? Yes. Yeah, so coming back to the slides, so as I said, the notebooks are really extensive and they're from first principles. So I encourage you to take the time to kind of go through them if you're interested. So coming back, the Gluon we saw is easy to program. It gives you high efficiency. It gives you a lot of flexibility to move across platforms. I just want to point out, in summary, this is kind of combining the best of all the worlds, right? So we saw the imperative was the preferred style of programming because it's easy and flexible. Even a beginner programmer can do it easily, right? The symbolic is, on the other hand, the one with good performance because you have the computation graph. And Gluon is able to give you both, combine best of both the worlds. So I just want to point out one more thing, in terms of running machine learning on the AWS cloud, we are making it easier and providing tools that kind of make it seamless for data scientists to run, right? So one of them is this deep learning army or the Amazon Machine Images. So the idea is, so how many of you use AWS? Okay. So how many of you use it with deep learning? Yeah, so quite a few. How many of you were aware of the army?
We saw it last week, actually.
Okay, so it's good it's being told about. I mean, the idea is very simple, right? So each time you spin up a cluster, if you have to go and install all the libraries, like kind of really set up everything, it's it's a manual process. It's not something anybody enjoys doing. And so by having the army, you can directly everything set up for you. So the idea is the NVIDIA and the MKL libraries are there, and all the deep learning packages are available, MXNet, TensorFlow, Caffe, PyTorch, so everything is available, so you don't have to do it. So this is one thing that makes it quicker for you to get started. The other are CloudFormation templates, so they're already templates that set up the cluster. So those also help you speed up starting your deep learning on the cloud. So I want to make one comment that Gluon is not yet available on the army. But you can just do pip install after the army, essentially do an update, and you would be able to get the Gluon version. But yeah, write to me if you have any trouble doing that. Yeah, so now I want to switch gears and talk a bit about going forward, right? What are some of the frameworks, like we've seen these number of architectures. Are there other principles we can use to come up with new architectures, potentially have savings in terms of parameters, so have more compact networks? And we'll see tensors will be one framework to do that. And this will also be important, especially as we have multiple modalities and we want to learn together. Could be visual question and answering, could be video, right? So there are now more dimensions. How do we exploit that in a good way? And so that's really where tensors come in, that our world is inherently multidimensional, and why stop at matrices? Right, so we are all aware from scalars, you get vectors to matrices, but tensors is what kind of covers everything beyond that as well, right? And if you think about even your standard convolutional network, right? So that's really processing tensors. So your image is three-dimensional, right? So you have width, height, and a number of channels, and as you send it through these convolutional layers, you're adding more and more number of channels. But with max pooling, you're reducing the width and height dimensions, your spatial dimensions. And so, in a way, we are processing tensors, but still we are using matrices to do the actual computation. So what I want you to think now is, can we treat them as tensors all the way end to end, and think of newer ways to process this? And so that's where we'll see how tensors can change our way of thinking, right? So the first one is a simple framework. It's called tensor contraction, or even tensor products. The idea is it extends matrix products, right? So with the matrix, you can multiply on the right or the left, and the multiplication process, it's very well defined, right? So it's pictorially, you can see here, you're multiplying the matrix with this vector. What you're doing is taking linear combinations of the columns of the matrix, right? So this is another kind of viewpoint of this being a linear operator, right? So now with tensors, you can do the same, but you have many more dimensions. So this is three-dimensional now, right, or order 3 tensor, and now you can multiply in 3 directions. So in this example, I've shown only multiplying with 2 directions, and what you're doing is you're taking multilinear combinations of these coefficients of your vector that you're multiplying. And so this is more generally known as tensor contractions, because now you can multiply tensor with multiple dimensions. This can be quite general. I mean, in this example, I multiplied with vectors. You can multiply with matrices, you could multiply with tensors, you could multiply simultaneously across multiple dimensions. So it can get as complex as you would like it to be, right? And that's really the richness of tensors. Now, with these more dimensions, you can think of doing multiplications in many different ways. So this vastly increases the domain of computations we have under our belt compared to matrices. So another popular notion with tensors is the idea of decompositions, right? So we're all aware of how to decompose a matrix, right? Singular value decomposition, or SVD, means that you take your matrix, you try to decompose it into its rank 1 components. Now you can do the same with tensor. So you can try to decompose it into its rank 1 components, and that's called the CP decomposition. So again, the richness of tensors means there's more than one form of decomposition. So the notion of matrix rank has multiple definitions, whereas in a matrix, they all just become the same, right? So they kind of fold all into the same notion. So this is, again, another richness of tensors, that we have different ways to think about decomposing this. And so this gives us a rich set of representations. We'll see another framework known as tensor sketches. So the idea is, as you're kind of obtaining these larger tensors, right? So it's also growing. Like as you add more dimensions, the number of entries grows exponentially, right? So and now with third order, you have cubic number of entries, right? So you may not want to store all of this, or this is something as a result of your processing. So this is an intermediate step. So you don't want to form this big tensors. And one of the new areas of research is how to do the sketching. So sketching means a dimensionality reduction. So, meaning you don't express the full tensor, can you give a reduced dimension tensor? And I'll show an example with visual question and answering. So you have the image, you have the question, you have to generate the answer. And what you do is you take the image representation, the text representation, and do this pooling and sketching that will help you avoid a blow-up of dimensions, right? You don't want to expand it to large dimensions. At the same time, it helps you look at higher order moments, cross moments between image and text features. So there's a number of things, interesting things you can do with tensors. So one of the first things we can think of is, as I said, right, so how do we enable tensor computations in our existing network architectures? So this is the classical AlexNet. I think all of you have seen this architecture, right? So you take the input image, you send it through a convolutional layer. With max pooling, you have the reduction of your spatial dimension, but with convolution, you have the increase in your number of channels. So you go through these convolutional layers, then you do this fully connected layers in the end, all right? But what's happening is when you go to these fully connected layers or dense layers, you're flattening this. So you're losing all the spatial dependency and just compressing this, right? Or rather flattening it into a vector. And these also tend to be very expensive layers in these architectures. And so the first question we asked is, why do you need to do the flattening? Right, because we're doing the flattening because we want to do a matrix product, right? You want to multiply this vector with a matrix and then go forward. But what if you retained it as a tensor and did tensor operations? And so that's the first thing we proposed. This is taking so from the convolutional layers, you take your input tensor, the activation tensor. Now you can do multiplication or contraction across all the dimensions. So you're learning weights across all the dimensions, and after this output, you could do some nonlinearity like ReLU and do these multiple layers. And on the right here is the symbolic graph in MXNet. I think there was a question earlier on how to visualize symbolic graphs, so this is one example, like you can automatically generate these graphs. And so this is a simple implementation. You can execute this by, kind of just converting it to a matrix operation, right? So you multiply your first weight here, you multiply the weight in the other dimensions by essentially doing the transpose. So this is a simple way to define the operator, but indeed there is a lot of room for further optimizations. So there are some other papers we've been looking into that, but for now, the idea is you can define a tensor contraction layer instead of your standard fully connected layer. And what we saw is, the full graph is in the paper, but what I want to point out is you get a huge amount of space saving with almost no drop in performance, right? So on BGG, about like 66% space saving, meaning smaller number of parameters in the fully connected layers compared to just a negligible drop in performance. And so the idea is by retaining the information about the spatial dependencies of these activations, you gain a lot. Yeah.
Is there an introduction in computational cost?
So yes, if it is done like very optimally, there is, right? So at the moment, as I said, the operator we define is in a suboptimal way because each time we're doing transpositions and so on. So some of the other work that I've done, kind of I can briefly point out, will also is addressing the performance. Good point.
Question. Taking you back,
Yeah.
How do you deal with the non-uniqueness of the rank of functions, or do you just ignore them?
So, in this case, we are not doing the decomposition, right? We are essentially doing multiplication. We are projecting along these weight matrices along each of the dimensions. So, it's really like the rank is, in terms of these dimensions, you're doing the reduction, right? So we are not directly doing any decomposition here. Yeah, so it doesn't matter here. Any other questions? So this was with respect to the intermediate fully connected layers. So for the last layer, the output layer, you can again do further optimizations, right? So in a standard network, what you get is this, the softmax layer. So again, you flatten, you multiply with the weight matrix. So what you can do instead is also parameterize the weight matrix as a tensor, right? So you can have the weight as a tensor, and you can make it low rank. So the rank here is Tucker rank, meaning there is a small core tensor, and there are factors that expand it to the required dimension. And now this is one of the coordinates of the softmax layer, so you do the inner product. So for all the coordinates, you can similarly have a range of weight matrices, and you can do these inner products, right? So this part is similar to what was there before. The only now new aspect is we're also parameterizing our weight matrix as a low-rank tensor. So by the way, like people have earlier tried to parameterize the weight matrix as a low-rank matrix, right? So if you just had a matrix weight and you try to do low-rank approximation, it's quite terrible. Like the drop in performance is huge. You try to reduce the rank by any amount. But with tensors, again, the richness of tensors means you can have a low-rank matrix. You can have a low-rank tensor, but if you flatten it as a matrix, it's full rank. Right? So you can now have these parameter reductions without sacrificing on the matrix rank. And that's what we see in this plot here, that it's really flat for a large portion, right? So you can get this, I think, was on the ResNet. What we see is you can have as much as like 70% reduction in your parameters on this layer and almost have no drop in performance. Right, so you can get now this huge amount of compression without losing performance by coming up with better architectures that preserve the spatial information that's present in images end to end. Right, so previously it was only being done in the convolutional layers, but now we do it all the way to the end. Any questions here? So I have about 15 minutes, so I had a lot more material. I think I was over-ambitious in terms of what I could cover. So I hope you don't mind. I'll just kind of quickly run through and give you only the high-level ideas. I think there's still some very interesting things here. So, I mean, maybe I'll skip this part and just get to the, yeah, so this was like a different framework looking at how to speed up computations, right? So this appeared in a HSPC conference, and the idea was, what new primitives can we describe for doing these tensor contractions? So this is looking at speed up. And the new primitive is called strided batch gem. It's present in CUDA BLAS 8.0. So I'll encourage you to look at the paper on how this does better tensor contractions, faster tensor contractions compared to the existing frameworks. And this is really about extending the BLAS operations, right? So BLAS 3 is the matrix multiplication, and now we are extending those kernels. And this leads to speed up when you're doing, for instance, Tucker decompositions, or even when you're doing FFT. So there is a multipole method for FFT that does tensor contractions. You know, tensors are everywhere. And so these, going back and asking what are new primitives we can define, can we extend our existing BLAS kernels, can really help us speed up a whole range of operations. But this is quite a tangential topic, so I won't give the techniques of how we did that. So I want to cover these tensor sketches in a little more detail. As I said, the idea is we want to think about looking at cross moments between our image and text feature. And so this is where now the tensor sketching is, like it's asking how I should combine these two features and still retain it to be a small number of dimensions, right, not blow up. I mean, the simplest thing what people do is take the, each part of the image feature, right, so each fiber or each vector here, take the text vector, concatenate them, and just, then do the forward process. So that's the baseline, so you just do the concatenation. But what the sketches do is do like kind of outer products or cross products across these vectors, or ultimately across these tensors themselves. So the idea is you're now generating higher order moments between your text feature and image feature, right? And this can be quite useful when you're trying to do complex tasks like visual question and answering. So I will kind of show you the notebook rather than talk about the details, because that will, I think, help you also, see the benefit of this, and you can go and actually work with this. So this is my student Yang Shi. I think it should be soon merged to the deep learning, the tutorials themselves, but I think right now it's in her repository, so if I can send out these links if there's interest. So the idea is, there is the VQA data sets, right? So you can, look at the image and look at the question and answer pairs. And so the idea is for generating image features, you can use any of the pre-trained networks such as ResNet or VGG. And you can also generate text features through a number of mechanisms. Either do word embeddings, you could do skip thought for sentence embeddings, or you could also use a pre-trained a neural machine translation encoder and use that embedding for getting the text features, right? So there is more details in another notebook on how you generated that. And so again, we're defining the model here. So these are just basic, like kind of setting the path size and so on, and defining the network here, right? So So you're creating like the batch norm, the dropout, and fully connected layers. So in this baseline, what we're doing is we're doing the concatenation, right? So we're taking the image feature, the text feature, concatenating them, doing some fully connected layers and dropout. I mean, this is not the state of the art, but this is the baseline, right? So this is something very easily you can cook up. And so now the count sketch is coming in the second part, where instead of doing this concatenation, you can now do sketching. So you're taking the image feature, the text feature, right? So essentially the outer product is what you would like. So this is like now looking at the cross moment between image and text features. But this, if you took the full outer product, that the resulting dimension is the product of the two dimensions, right? This is way too big. You don't want to then have layers after that, right? So what this sketching does is, it at the same time, it does randomized dimensionality reduction. So it gives you some compressed representation of these outer products. And the details, the mathematical details are in the paper, but like using FFTs or fast Fourier transforms, you can do this in a very fast manner. And this is again the Gluon implementation of that. So there's now a new count sketch operator, and that essentially does this for you. Like this is defining like count sketch on the individual text and image vectors, doing FFT and doing product of FFT, and you could do the inverse FFT, and that essentially does the operation. So, and these hashed tables are for randomization, right? So it's really like kind of this very short piece of code that can now enable sketching now outer products of image and text vectors, and at the same time doing the compression through the sketching process. So there are more details, but I'll encourage you to look through the notebook. And so that's the idea, that with this very simple framework, you can actually get this model that can now take a test image and come up with what the answer is. I think the question here was, what are the walls made of? And the answer, at least in this example, was the correct one, that is the brick. So I encourage you to look into the notebook, because you can also try out with different data sets or different examples and see how this is implemented.